I'll just do a little recap. Okay, yeah, so you're joining us in progress. if you're watching the video, we've taken a function and we're going to write the tangent line to it. The way we're going to write the tangent line is we're going to find the point that goes with a particular x, find the y that goes with that x by plugging that x into the original function. And so e with a 2 plugged in for x became e to the 0, in this case, or 1. We're now in the process of figuring out the slope of the line. And the way we're going to find the slope of the line is we're going to use the derivative of the original function with 2 plugged in. Now, since we've got our new style of function, exponential function, not new, but new for calculus purposes, the way we take the derivative of e to a function is we basically leave it identical. The derivative of e to some function is e to that function, but then the derivative times the derivative of that function. So the reason we got that here is that's the derivative of x squared minus 2x. So e derivatives can look really intimidating. They're messy, but one of the things you'll always see in an e derivative is the original e expression coming right back at you. Here's the function, here's the derivative with that times its little piece for chain rule. Okay, so if I plug a 2 into that, that's 4 minus 4, and that's 4 minus 2. Once again, I'm not going to get super freaked out that I have to evaluate things with ease. We're not in pre-calc where I've taken your calculator away. We're not in AB where I'm not letting you use a calculator. You can absolutely type these kinds of things in your calculator if you want. Oops. Yeah. I mean, I would hope that, that wasn't necessary, but if it is, it is. So e to the 4 minus 4 or e to the 0 equal to 1. So e to the 0 times 2, or 1 times 2 is 2. So we've generated the slope of our tangent line. We have a point, we have a slope. I'm going to add a page in, but I'm going to move it here. So my point was 2, 1, and my slope turned out to be 2. So my tangent line is, here we go, y minus 1 equals 2 times x minus 2. Now, how we can get any sense of that, if that's right or not? Well, we can get kind of a visual sense if I look at the original function and then look at the graph of that function with the tangent line graphed on the same axes, I should always see, thank you, something that looks like this, where I have the original function curve, and then wherever I've drawn the tangent line, it should just be kissing that curve, and you should be able to identify that they intersect. And Desmos does that really nicely for you, because when you click on it lights up the point. So yeah, so now it lights that up. Hey, 2, 1 is the point where they connect. And that's the only point where they connect. If you zoom in, you'll see it's a little minuscule, but they are separated. And because it's hard to even see that they're separated, that's one of the reasons that the tangent line is a good approximator. If I wanted to know the y value on the red curve about here at an x that's pretty close to 2, this y value, actually, sorry, that y value compared to that y, it would be a pretty good approximation. It'd be even better the closer we are to 2. The closer we are to 2, the closer the two functions are to being identical. And so that was what one of the things Newton talked about with his concepts of calculus, that linear functions, like this blue one, could approximate nonlinear functions in small sections. So let's say you did, like, mess something up and you did like that, you know, you'd know that wasn't right. That's definitely not a tangent line. That line is crossing that curve in lots of places. You know, if you, maybe we put the, maybe this is wrong. Okay, once again, definitely not a tangent line. A tangent line should snuggle right up against the curve. Just touch it at that one point. So, you know, if you're off by just a little bit, you may not see it, but you know, most of the time what happens is you do something kind of way off. You're like, oh, wait, like that's not even touching. Clearly something's wrong with my line. Oh, I put, you know, +1 instead of -1. Okay, so using what we did last time with the derivative, using Unit 2 concept of writing a tangent line, we've now extended this application to an exponential function. All right, let's try another one. I'm actually going to throw another little, no, we'll do that for the third one. Let's see. Let's go back to single page. Okay. And let's do this one. I want to do one where it doesn't always, everything doesn't come out so pretty, of course. So how about, let's do this. Ooh, I wonder what that's going to look like. Okay, that's fine. All right, we'll do that. And we're going to do the tangent line at x equals 0. So after you write that down, why don't you go ahead, let's not do the derivative yet, but find me the y that's going to go with that x. Meanwhile, I'm going to do a little graphy graph here. What's the y going to be in our point? That's interesting. Okay, here, let me. What happens when it's like, is it just super big? Oh, poop. Where'd my function go? Here he is. Where's my x-axis? Where's my y-axis? Did I turn the axis off? Oh, duh. Okay. Well then, we're just gonna get super big. Is that gonna... It's interesting. Oops. It's kind of the fun thing about Desmos is because you can just do like sort of random things, and you can, it's a lot easier to adjust the window to sort of see what's going on. Let me do a lot less X's and a lot more Y's. Okay, that's better. You can kind of see it. So this is what, oops. This is what that looks like. Okay, it actually just kind of looks like an exponential curve, but it's moved up. I think it's gonna continue to be asymptotic. It looks like as I keep scrolling this way, it is getting closer to the x-axis. But we're not going to cross it. And that's the interesting thing, is that if you look at this, okay, first of all, that's not going to give me very much, but when I scroll out, you can see that's kind of a weird turn, right? That's much sort of a different turn than when you start looking at it with a lot more. It's pretty abrupt. It's kind of more than you might see from just an exponential curve. So, but this is what our function model looks like. And so if we're looking at our x-axis or our y-axis where x equals 0, it looks like, yeah, we're gonna have a pretty big number here for y. Oh yeah, because when x equals 0, oh, this is messy. So my y would be 4 plus e to the 2 times 0, quantity squared. Okay. This is not what I meant, but that's okay. I'll do that on the other one. So 5 squared or 25. So 0, 25 is going to be my point, where we're going to put our tangent line. 0, 25. So yeah, so that's going to be all the way up here. Our tangent line is going to be really steep. It's going to have a really, really, really big slope. It's still going to be a positive slope because it's going to lie like this. It's going to touch this point and it's going to lie right there against it. But that's going to be a big old slope. All right, so let's see if we can see what that big old slope is going to be. I threw a little extra curve on this one. When you take the derivative of this particular function, we've got to go back to our chain rule idea. I've got a function, I've actually got a combination of two functions, all raised to a power. So when I take the derivative of this, I'm going to power rule around the inside, and then I'm going to take the derivative of the inside, and what's on the inside has an e, and that derivative, or the derivative of the 4 is going to be a 0. The derivative of the e to the 2x is going to be e to the 2x times 2. And if you prefer, I can probably write that. Should have actually. So it's going to look like this. Plus 2. A little bit of chain rule, derivative of the inside. And when I plug in a 0, we're going to end up at 4 plus e to the 0. And then 0 plus e to the 0 times 2. So that's a 5. And that's a 2. Looks like we're getting a slope of 20. That's a pretty big slope. Y minus 25 equals 20 times x minus 0. As awkward as that sounds, let's take a look at it. Wow. I mean, oh, it's hard to see. Let me give you even less x's. Less x's will spread it out more. Okay, so you can see the red curve, you can see the green line. They definitely intersect right there. The green line is coming down and touching the red curve. If we zoom in a little bit more, yeah, we've got a tangent line looking thing. They're distinct from each other. They do have an intersection. That's kind of a weird function, but I like to do that problem because I wanted us to review another derivative rule, namely the chain rule, having a function all raised to a power, so a function expression all raised to a power, and having to do that power rule sort of around that and then times the derivative of the inside. I'd say that's probably not as common of a type of function that you might play around with as something with a product or a quotient, at least for ease, but it's another variation that we should be able to do. We should be able to take the derivative of anything I give you, fitting product rule, quotient rule, chain rule, that also has an e in it. All right, one more. Let's do a quotient rule this time. Oh, yeah, I like this one. I have one from last class. This one I think will be a little prettier. Well, no, not prettier, but it'll be, I don't know. That one was like kind of a weird looking graph. Let's take a look at this guy. So here's my function for this one. I'm going to look at x squared plus 3 over 2e to the 3x. And let's do I'd like this to not be, I'd there to be e's in it. Oh, I'm gonna have to do that then. Nope, we'll just stay here. We'll stay here. It'll be okay. Let's do that one. Tangent line at x equals 0. Should have changed that second problem. well, that's okay. To e to the 3x. Oops. Is that what I wanted? I guess I did. Okay. Yeah, we should have done that product one. It's okay. That's okay. We'll do this one. Huh?
Quick question.
Uh-huh.
We're doing the quotient rule.
Right.
Top is f times g prime minus g times f prime, or is it the other way around?
It's gf prime minus fg prime.
I
Okay.
was just making sure.
Yeah, that's all right. And I'm sure you're not the only one that's worried about think about that. So quotient rule again, gf prime minus fg prime over g squared. When we do the quotient rule to find the derivative, and that is me looking at this as the numerator being f and the denominator being g. So some people think about it as high and low, and you start down low, so you start with the 2e to the 3x. You start with what's in the, so the denominator times the derivative of the numerator, numerator derivative of denominator, subtraction instead of addition, and then with the g squared. We'll need that for the slope, but we'll also just need straight substitution to get the point. Now, little things like order of operations can throw us off, especially on something like the denominator. If you think, oh, I'm going to go left to right, you're like 2 times e, but then raised to the 0 power is going to equal 1. The way you have to think about it is that 0 power, the 3 times 0 equals 0, that 0 power on the e applies first and then times 2. So my numerator is going to be 3. My denominator is going to be 2 times 1. That's going to make my denominator 2, which is going to make my y, in this case, 3/2. If you're uncomfortable, you can absolutely put that in your calculator. You just have to be really careful about numerator and denominator if you're using a handheld, that you've got the groupings done together. Desmos actually does stuff like that really nicely. If you haven't played with just doing calculations on Desmos, that's one of my favorite things about it, is if you start doing something like oops, sorry. Let's go here. Okay, so 0 squared plus 3, and then you hit divided by, oops, no it didn't. I thought it would automatically jump to it. Sorry. I don't know what I was doing from before, but maybe highlight it and then, no, maybe not. Okay. You might have to use some parentheses. There you go. And then divided by, and it will go ahead and do that for you. Also, remember E on Desmos is just the E from the keyboard. It understands that you mean the numeric E. You also have to make sure you got things up in the exponent times 0. 0. Oops. See, if we put it in the wrong place, though, I can't get it to stay up there. Maybe if I do. There we go. Also, I haven't really used it, but Desmos does just have a, I don't want to get rid of this now. No, go away, go away. I don't want you there. There we go. Desmos does just have a graph or a non-graphing. It's just a scientific calculator. So I would say probably input's about the same. So 0, 1.5. Once again, we can see that that happens to be the y-intercept. When x equals 0, the y is 1.5. That's where my tangent line's going to go. Zoom this in a little bit. What should happen this time is my tangent line slope should come out negative because the line is the curve is curving down this way with upward concavity. So the tangent line is going to sit over here and have a negative slope. Okay. So I'll expect that. When I write my derivative, it's going to be the denominator times the derivative of the numerator. Shrink this down a little bit. All right. So my denominator function times the derivative of my numerator function minus my numerator function times the derivative of my denominator. Now, 2e to the 3x, derivative of that, 2e to the 3x is in there. 2e to the 3x, but times another 3. 2e to the 3x times another 3.
Wouldn't that be 6e?
So which would be 6e to the 3x. So yeah, so you can write 6e to the 3x, or you can write 2e to the 3x times 3. Be the same. I'm going to erase this for a second. I'm just kind of just want to just keep emphasizing the idea that when we take the derivative of an exponential, we get the identical exponential back times the derivative of whatever function's in the exponent. So 2e to the 3x times another 3, and then that's going to be over 2e to the 3x quantity squared. Now, luckily, we do have a calculator to help us kind of get through these computations. Every little section, you might want to kind of address it individually. So when I put a 0 in for x, I get a lot of that, okay? So 3x in the exponent becomes a 0. The 2x sitting next to that becomes a 0. X squared plus 3 becomes 3. 2e to the 3x becomes 2e to the 0 times 3. And then the parentheses, super important in the denominator, 2e to the 0 quantity squared. So this big whole chunk ends up as 0. This ends up as 3 times 6. Because it becomes 2 times 1 times 3 in those parentheses. And this is going to be divided by 4. It's a little fun. And so what happens is you end up with negative 18 over 4. Or negative 9 over 2. Making sure you're practicing this kind of computation as we're going through a problem, making like I'm doing it for you, so you're just writing it down, but you know, making sure you can actually pick up your calculator and take something like this, create something like this, and then evaluate it for a 0. You gotta be careful. You gotta watch all your steps. You might need to just use some grouping symbols. I tend to do better if I try to do this a little bit at a time and write down my work. I know you guys sometimes will try to do this as one big chunk in the calculator. Very more likely you're going to make a mistake if you do that. I recommend little chunks. You know, 2 times e to the 3 to the 0 times that. And even sometimes writing it down, you're like, okay, I don't need to type that in my calculator. Something like this times 0 is going to make it 0. Okay. So that's my slope. So here's my line. Now, none of the ones I did had us end up with something in terms of E. That's unfortunate. I shouldn't have skipped that one problem, but that's okay. You may have that happen. And if you do, it's just a matter of, like I said, you can just leave the E. Like if you end up with E squared, you can just leave E squared as a value. Or if you want to replace it with a decimal, you can. X minus, 0. Okay, so there's the line. And, oh. What did I do with that? Where did my graph go? Did I mess that up? Okay, there we go. Oh, because I deleted that one. Okay, I deleted the one. There's my graph. There we go. I want to see if this looks right. Y minus 3 halves equals -9 halves. I guess it likes it when it's just a number to make the fraction bar x minus 0. Okay, there we go. Looks pretty good. Curve, tangent line, 1 point of intersection. Zoom in, you can see getting pretty close together, just touching right there. I'm in good shape. Okay, so to follow up with what we just went through, I'm going to ask you to do a few problems as practice/homework. I've already copied the page. Actually, let's go here. Here we go. Yep, we can leave that. We don't need you. So if we go to 4th period, and I'll pull this up in front of you, and materials, I already copied this over. I need to just change the date on it. This was when I dated it from yesterday's class for 7th period. So this is page 273 out of the textbook. February 1. And I will write this in the notes as well. When you go to this page, we're going to find this little tangent line section. And they've actually done a really nice job for you. They've actually figured out the full point for you. Your job is to do problems 22, 23, and 24. So you write the tangent line equation to each of those functions at the given point. So, nice thing is, you actually don't have to worry about the y value, because you've got that. You've got the x and you got the y. You primarily have to worry about the derivative to generate the slope to ultimately make the tangent line equation. 22, pretty basic. 24 is a quotient rule. 23 is a product rule. Since we practiced product rule on homework, that shouldn't be so bad. I think I was thinking we were going to do 25 or 26. That's why I pulled a chain rule out, but We're just going to do these three. So 22, 23, 24, finding the tangent line equation. Let me pull this over here. Let you do that. And that's where we are for now.